Assalamu alaikum. I'm Hafiza Nageen Yousuf. I am from MS Chemistry Batch 1. I will present about the topic Organometallics. These are the contents of my presentation, which includes introduction of the organometallic, importance of organometallic field, industrial milestones in the organometallic chemistry, electronic applications, organic synthesis, catalysis by organometallics, homogeneous catalysis, and hydrogenous catalysis. First of all, introduction of organometallic compounds. Organometallic compounds are those compounds in which central metal atoms are directly bonded with the carbon atom of the hydrocarbon radicals or the molecules. Basically, in organometallic compounds, metal atom form the bond with carbon atom of the hydrocarbon compound. The bonding is ionic or covalent or delocalized between the organic groups and the metal ion. First organometallic compound which was isolated was Z-salt, which which formula is potassium trichloroethene platinate 2. Organometallic compounds belongs to the coordination compound. Organometallic chemistry is the subfield of coordination chemistry in which complex contain metal carbon bond, which is one of the example of organometallic compounds which is also belong to the coordination compound are the carbonyl compounds. Carbonyl compounds form bond with the metal atoms, which are organometallic compounds. Organometallic species tend to be more covalent and the metal is often more reduced than in other coordination compounds. Basically, in organometallic species, metal atom is more reduced as compared to the coordination compound. Typically, ligands that usually bind to metal in their low oxidation state are carbonyl, alkenes, and arenes. Carbonyls are the basic ligand which form the organometallic compound. Importance of organometallic field. The organometallic field has provided a series of important conceptual insight, surprising structures, and useful catalysts both for industrial processes and for organosynthesis. One of the main function of organometallic compound is their catalytic activity. These catalysts used for both industrial processes and the organic processes. The field is beginning to make link with biochemistry with the discovery of enzymes that carry out organometallic catalysis. Basically, organometallics also found in the biological processes. One of the example is acetyl-CoA synthase, which is an enzyme based on an organometallic compound. Ideas drawn from organometallic chemistry have helped interpret the chemistry of metal and metal oxide surfaces, both key factor in heterogeneous catalysis. Organometallic compounds are able to carry out heterogeneous catalysis as well. One of the example of the heterogeneous catalyst is Ziegler-Natta catalyst. The field is also creating links with the chemistry of materials because organometallic and the metal organic compounds are increasingly preferred as a precursor for depositing material on various substrates. Most of the organometallic compounds are also used as a precursor for many substances. These can be used as a precursor for depositing material on a surface by using the method of thermal decomposition. Nanoscience and the nanotechnology, which is very new technique, also using organometallic compound as a precursor. These small particles of a metal are alive with properties quite unlike the bulk material, are finding more and more useful application in electronic, magnetic, and optical devices or in sensor. These nanoparticles also used organometallic compounds as a precursor. Industrial milestone in organometallic chemistry. The three major types of applications of organometallic compound in industry are in the area of electronics, polymers, and organic synthesis. In organic synthesis, the organometallic compounds are used as either catalysts or stoichiometric reagents. First application is electronic applications. For electronic application, typically the organometallic complex is subjected to chemical vapor deposition. to form an appropriate thin layer are subjected to organometallic chemical vapor deposition, where the deposition ultimately occurs through a chemical reaction at the substrate surface to produce a high quality material. Basically, organic metallic compounds are used for the electronic application to produce a high quality material. The production of thin films of semiconductor material is used. For example, for LED applications through metal organic vapor phase epitaxy, these are the techniques which are used to make electronic um, electronic devices which use organometallic compounds. They react with ultra pure gaseous hydrides in a specialized reactor to form semiconducting product as a crystalline wafer. Second application of organometallic compounds is polymer. Another major application for organometallic complexes is in the polymer industry. Three common type of polymers produced by catalysis are particularly noteworthy. First one is polysiloxane, also known as silicone or polymer made up of repeating units of siloxane. A milestone in the history of organometallic chemistry in the industry was the discovery of Ziegler-Natta catalyst, and its application is polymerization reaction. Basically, Ziegler-Natta catalyst used for the heterogeneous catalysis. Another area that has been recognized for its importance is olefin metathesis. Metathesis is basically a transfer reaction which which occur for the alkenes, which also uses organometallic compounds, for which a Nobel Prize has been awarded to Grubbs, Schrock, and Chauvin. This has been applied to synthesize polymers through ring opening metathesis polymerization process. One of the main application of organometallic compound is also activation of carbon monoxide and the carbon dioxide. Most organic chemicals are currently made commercially from ethylene, a product of oil refining. It is possible that in the next several decades, we may have to shift towards the other carbon sources for these chemicals as depletion of our oil reserves continues. Either coal or natural gas can be converted into carbon monoxide or hydrogen mixture, which is basically water gas. A mixture of carbon monoxide and hydrogen is called the water gas or the synthesis gas, and which can be converted into methanol or to alkene fuels with using various heterogeneous catalysts. These heterogeneous catalysts are organometallic compounds. In particular, the Fischer-Tropsch reaction converts synthesis gas to a catalyst of long chain alkenes and alcohol using heterogeneous catalysts. These catalysts are metal based, which are usually organometallics. This is the reaction where the synthesis gas is produced using heterogeneous catalysts which are organometallic based. These when synthesis gas is produced, which is further reacted to form alkanes, long chain alkanes and alkenes in the presence of organometallic catalyst. Water gas shift. It is often useful to change the carbon monoxide and hydrogen ratio in the synthesis gas, and this can be accomplished by the water gas shift reaction, which can be catalyzed heterogeneously or by the variety of homogeneous catalysts such as iron carbonyls, which are iron carbonyl is an organometallic compound because it has a bond between carbonyl group and the iron. So we can change the ratio of carbon monoxide and hydrogen in the synthesis gas using organometallic compound. The reagents and the products have comparable free energies. The reaction can therefore be run in either direction, and this can be regarded as both carbon monoxide and carbon dioxide activation. This is the cycle proposed for the iron carbonyl catalyzed water gas shift reaction. In this reaction, this is the catalytic cycle which carried out in the water gas shift reaction. First of all, hydroxyl group is removed, and then the carbon dioxide is removed, and resultant we produce an activated form of a catalyst which involved in the water gas shift reaction. Mechanism. In the previous slide, the reaction present here is its mechanism. In the mechanism proposed for the homogeneous iron catalyst, carbon monoxide bind to the metal and so become activated for the nucleophilic attack by the hydroxyl ion at the carbonyl carbon. Decarboxylation of the resulting metallocarboxylic acid probably does not take place by the beta elimination because this would require prior loss of carbon monoxide to generate a vacant site. Instead, deprotonation may proceed loss of carbon dioxide followed by the reprotonation at the metal to give activated form of the organometallic compound. Protonation of this ionic hydride liberated hydrogen and regenerate the catalyst. Next application of the organometallic compound is organic synthesis. One of the major applications in organic synthesis is catalysis. The reactivity of the organometallic complexes towards various reagents is the reason behind the widespread use of organometallic compounds as catalysts for a variety of organic transformations. The most important types of organometallic reactions are oxidative addition and the reductive elimination. The oxidative addition of hydrogen onto viscous complex, which is shown, viscous complex is shown in the reaction. Viscous complex is a crucial step in a metal catalyzed hydrogenation reaction. Catalytic cycle. The catalytically active species must have a vacant coordination site to allow the substrate to coordinate. So organometallic compounds have such vacant coordination sites, so they perform more efficiently the catalytic activity. The establishment of a reaction mechanism is always a difficult task. It is even harder to definitely establish a catalytic cycle as all the reactions are going on in parallel. Mostly late transition metals are privileged catalysts. So late transition metals make organometallic compounds and which can perform catalytic activity efficiently because they have vacant coordination sites. In general, the total electron count alternates between 16 and 18. One of the catalytic steps in the cycle is the rate determining step. First of all, catalyst precursor, it get activated. After activation, then it reacts with the substrate and the reaction proceeds. Fundamental reactions. There are some fundamental organometallic reaction types to describe multi-step catalytic cycle. Basically, organometallic compounds does not catalyze reaction in the one step. It occurs in a series of steps. Different steps are included in the catalytic cycle. These are steps: ligand dissociation or association, oxidative addition or reductive elimination, hydrogenolysis, four-center concerted reaction, and hydrolytic hydrogen activation, migratory insertion or elimination, nucleophilic electrophilic reagent attack, and a coordinated ligand. These are the steps which are followed in the catalytic cycle. Either catalyst undergo the ligand dissociation or association, oxidative addition and reduction, hydrogenolysis, migratory insertion, elimination, or nucleophilic or electrophilic reagent attack on a coordination ligand. Then the mechanistic concept. The fundamental reactions are involved in the following steps of the mechanistic cycle. Basically, mechanistic cycle involve following steps, which includes activation of catalyst, reaction on the metal center. First of all, catalyst get activated, turns into its activated form. Then it's reactive with the metal center, and then they release the product from the metal center. So activation of catalyst includes coordinative unsaturation, generation of vacant site to accommodate incoming reactant. When activation of catalyst means creating a vacant site to accommodate incoming reactant. Reaction on the metal center. Reaction on metal center occur by alkyl migration or the migratory insertion. Release of product from the metal center. Product is released from the metal center by the process of reductive elimination or the beta elimination. Beta elimination usually occur in the alkene compounds. Next are the types of catalysis: homogeneous catalysis and heterogeneous catalysis. Organometallic compounds are able to perform both homogeneous and heterogeneous catalysis. First, we will discuss about the homogeneous catalysis. Homogeneous catalysts are used when the selectivity is critical and the product catalyst separation problem can be solved. When we want a very selective product, then we use homogeneous catalysis. Catalytic step in homogeneous reactions: most catalytic process can be built up from a small number of different types of steps. These are the steps: association and dissociation, or dissociation of the ligand requires a labile complex, insertion and elimination reactions, nucleophilic attack on a coordination ligand, oxidative and reduction of a metal center, and then oxidative addition and reductive elimination. One of the main homogeneous catalysts which belongs to the organometallic class is the Wilkinson catalysis. Wilkinson catalyst is a triphenyl rhodium chloride complex was the first highly active homogeneous hydrogenation catalyst. This catalyst is used for the hydrogenation reaction and was discovered by Geoffrey Wilkinson in 1964. Wilkinson's catalyst is a rhodium 1 complex. It contains 3 phosphine ligands and 1 chlorine and the rhodium metal. As a result of the olefin insertion hydrogen migration, we obtain rhodium 3, which contains 16 electrons, 5 coordinate species. A solvent occupies the 6th coordination site to take it to a 18 electron species. Reductive elimination occur to give the hydrogenated product and the catalytically active species. Olefin hydrogenations using Wilkinson catalyst. Wilkinson catalyst used for the hydrogenation process. The complex Wilkinson catalyst became the first highly active homogeneous hydrogenation catalyst that compared in weights with heterogeneous counterpart. In this reaction, one octane reacts one octanes undergo hydrogenation in the presence of Wilkinson catalyst and resulting product octane is formed. Hydrogenation mechanism. Hydrogenation mechanism consists of 4 basic steps. In first step, hydrogen is added. Addition of hydrogen occur. In the second step, alkene addition occur. In the third step, migratory insertion is occurred. And the fourth step includes the reductive elimination of alkane. The resulting our product in the fourth step, our product alkane is released and our catalyst is regenerated for the further cycle. Then hydroformylation. The reaction of an alkene with carbon monoxide and hydrogen catalyzed by the cobalt or rhodium salts, which are basically organometallic compounds, to form an aldehyde is called the hydroformylation reaction. Hydroformylation was discovered by Otto Roellon in 1938. In this reaction, an alkene reacts with the carbon monoxide and hydrogen in the presence of rhodium and cobalt and produce 2 types of aldehydes. One is linear, another is branched. These are the steps of the hydroformylation reaction. First is the reduction. This reduction produces an active form of catalyst. The catalyst uses the carbonyl complex, which is organometallic compound. Then second step includes the ligand replacement. Ligand is replaced by the alkene. The metal atom is holding the reactive species together. And the third step is the insertion of alkene into cobalt hydrogen bond. Hydride hydrogen atom adds to carbon atom of alkene. Fourth step include insertion of carbonyl into cobalt alkyl bond. And the step number 5 includes reduction and the product elimination. Hydrogen adds oxidatively to metal complex and the product is then eliminated in a reductive elimination reaction. Hydroformylation process are OXO. This is an example of homogeneously catalyzed process. All the reactants present in the same phase. The mechanism illustrates several of the reactions summarized above. We have discussed the mechanism of the whole process in the previous slide. So overall reaction includes the alkene react with the carbon monoxide and hydrogen, and resulting aldehydes are produced. Aldehyde can be of different type, can be linear, and it can also be a branched form. Then Monsanto acetic acid process. Organometallic compounds can be involved in the formation of acetic acid. Over 2 million tons of acetic acid a year are produced by carbonylation of methanol, which happens in more than 99% selectivity with a rhodium catalyst. The active catalyst used is the rhodium catalyst, which is organometallic compound in which rhodium and the carbonyl has a bond. Carbonyl act as a ligand. The net effect is the cleavage of methanol carbon-oxygen bond and insertion of carbonyl. To be carbonylated, the methanol has to bind to the catalyst, and this requires adding a certain amount of hydrogen iodide to the system. In this reaction, alcohol react with the carbonyl in the presence of methyl iodide, and the resulting acetic acid is produced. Catalytic cycle for the Monsanto acetic acid process. In this reaction, first alcohol in the presence of methyl iodide and rhodium catalyst undergo oxidative addition, and then in the second step carbonyl insertion occur, and at the end reductive elimination occur, and our resulting compound acetic acid is produced. Next is hydrogenous catalysis. Hydrogenous catalysts dominate chemical and the petrochemical industry. 95% of all the chemical processes use hydrogenous catalyst. Ziegler-Natta catalyst for the polymerization of olefin. Polymers are large molecules with the molecular weight in the range of 104 to 106. These consist of small building units known as monomers. For example, polyethylene is made up of ethylene monomer. In all of these cases, a single monomer is repeated several times in the polymer chain. The number of repeating units determines the molecular weight of the polymer. And the Ziegler-Natta catalyst is used for the polymerization of alkenes, and the Ziegler-Natta catalyst is organometallic compound. The German chemist Carl Ziegler discovered in 1953 that when the titanium trichloride and triethyl aluminium are combined together, they produce an extremely active hydrogenous catalyst for the polymerization of ethylene at atmospheric pressure. Giulio Natta, an Italian chemist, extend the method to other olefins like propylene and develop variation of the Ziegler-Natta catalyst based on his finding on the mechanism of the polymerization reaction. The Ziegler-Natta catalyst family includes halides of titanium, chromium, vanadium, and zirconium, typically activated by the alkyl aluminum compound. Basically, Ziegler-Natta catalyst belongs to the halides, which consist of titanium, chromium, vanadium, and zirconium, and this catalyst is activated by alkyl aluminum. Ziegler and Natta received the Nobel Prize in Chemistry for their work in 1963. There are typically three parts to most polymerization. Most of the polymerization consists of three steps: initiation, propagation, and termination. Initiation includes generating the active catalyst from a less active catalyst precursor. In initiation, active catalyst is generated from a less active catalyst converted into active catalyst. Next step is propagation. The polymer chain growth portion of the reaction that occur over again and again. Propagation phenomena includes increasing the chain length. Next is the termination, a reaction step that stops the polymer chain growth. The termination step is the final step which stops the formation of polymer. These are the references where I extract the data. Thank you. That's all from my side.